Good morning. We've been discussing about the displacement method, and in the last few lectures I have established the basic concepts behind the displacement method, and I had promised that we'll spend about 3 to 4 lectures on looking at various examples in the application of displacement method. So today we are going to be starting off by looking at one particular example. Over the kind of way I've chosen the examples has been essentially to establish the key principles of the application of the displacement method, or actually the matrix displacement method, which is the stiffness method, as I had already stated. Next few lectures we're going to do that. Of course, it is impossible to do all types of problems, so I'm only going to be taking up representative problems, and along the way I'll illustrate a few detailed notes about the application of the displacement method which I have not set up in the thing. For example, how do we consider if we have a support settlement? Okay, how do we consider temperature stresses in the displacement method or the stiffness method? All these things I'll be taking up as examples as I go along during this particular few lectures, next few lectures. Okay, so let us start off with an example. I'm going to start off with simple examples and then go on to slightly more complicated examples. Okay. So let me take absolutely the simplest example. So this is the structure. This is EI 4 meters and this is 2 EI 5 meters. Okay, so this is the problem, and here the problem is essentially to figure out a displaced shape and also to figure out the bending moment, member end moments, and the bending moment diagram for this particular structure. Okay. First and foremost, how many degrees of freedom? Now I'm going to just state it, and I will expect you to find this out. This is 2 degrees of freedom structure. Use the procedure that I have developed and establish that these are 2 degrees of freedom. Okay. Of course, all of them are actually rigid. So the displacements are R1 and R2. Okay. So once we have those displacements, the next step is first to find out the fixed end moments. Okay. So the fixed end moments here, let me just go back to this. This is A, B, C. Okay. So fixed end moment for AB, the beam that I consider for AB is this one with this, and due to this you're going to have a fixed end moment at BA, and the fixed end moment at BA is going to be equal to 100. Of course the entire thing is minus, but 100 into 4 squared divided by 12. Okay, and plus 1/2 100 into 4 squared upon 12. Okay, so that is equal to 3 by 2 is going to be equal to 108. So this is going to be equal to if we look at this, it's going to be 100 divided by 4. Okay. It's equal to 8 upon, so it's going to be minus 8 200, and this is going to be 300. So this is going to be equal to minus 300 kilonewton meter. Okay. Now FEM BC is equal to FEM CB, which is equal to 0, because there is no member forces in this particular member. So having done that, what happens is the next step is going to be getting the displacement pattern for each one. So let us have a look at that. That's going to be R1 equal to 1. This is going to go in this way, come like this. Simple displacement pattern that you have. And if you look at it, what is theta BA equal to? Theta BA is equal to 0. Theta BC is equal to 1 upon 5 from, so that is positive 1 upon 5. Theta CB positive 1 upon 5. Then we have the rotation. The rotation is going to give me this. So this is going to give me theta BA. This is R1 equal to 1. This is R2 equal to 1. So theta BA is equal to 1. Theta BC is equal to 1. And theta CB is equal to 0. So therefore, if we look at it, what we have is A for member A, B is going to be equal to 0, 1. And A for member BC is going to be equal to 1 by 5, 1 by 5, 1, 0. What is A? A, if you look at it, is essentially, so VI is equal to AIR. So here what I have done is I have actually found out the two displacements, that the two kinematic relationships. The one that relates the member and rotation. Note that since I have a modified member, I only have theta BA as my member rotation, okay, and the relationship with the degrees of displacement corresponding to the degrees of freedom. Okay, so this, having found out this, we can say that, what do we have then? That we know that Si, which is in the case of SBA, AB, which is actually, you will see, is equal to MBA, because MAB is equal to 0, is equal to what? It is equal to this is A transpose, so it is going to be equal to 0, 1, R1, R2 minus 300. Okay, and SBC, which is equal to MBC and MCB, is equal to this into KBB, and this is equal to note that SI is equal to KI VI plus SI0. Okay, so in this particular case, the K is equal to 3EI by L. L in this particular case is 4. For this, the MAB is equal to 4EI by L and 4EI. Now EI is 2EI, so this is going to be 8EI upon 5 and 4EI by 5, 4EI by 5, 8EI by 5 into 1 upon 5, 1 upon 5, 1, 0 into R1, R2, and then plus 0. So this is our relationship, and ultimately using the displacement, the virtual displacement, we can find out that capital R is equal to sum of AI transpose SI, okay, plus, this is summed up over all the members, plus I into AI, this I am going to put it as transpose, into NI. These are the reaction terms that come from the member forces, the reactions only, because those are not considered in this specific thing. So if we put that in, what we get is that in this particular case, this will only exist for the summation AI into NI. This, in this particular case, is only in AB, because that is the only member force that you have, and the reactions that you have for this particular 100 kilonewton is 50 and 50. Okay, and if you look at these, the work done by these 50, so the AB transpose is actually equal to, you will see that in both the cases these are 0, 0, 0, 0. So the contribution, how much, in other words, what we are really trying to find out is, given R1 equal to 1, how much does this point move up by and how much does this point move up by. If you look at the displacement pattern, if we go back to the displacement pattern for r1 equal to 1, okay, how much does this point go up by? 0. How much does this point go up by? 0. In this particular case, how much does this point go up by? 0. How much does this point go up by? 0. So that is essentially what you get over here, and therefore this term, in this particular case, this term is equal to 0, because this is going to be equal to this into your Ni in this particular case are equal to 50 and 50. So that is equal to 0. Okay. So now what we need to do is essentially look at the other terms. Okay. So if we look at it, we get R equal to summation then AI transpose Ki AI into R. Okay, and the other term is 0. Okay, so I need to find out for AB what is AI transpose Ki AI. Now if we look at it, AI is equal to for AB is equal to 0, 1. Ki is equal to 3EI upon 4. Okay. So therefore, what we have here is, since Ki is a scalar, I can just do AI transpose into 0 into 1 into 3EI upon 4, and if you look at that, that becomes 0, 0, 0, 1, 3EI by 4. So therefore, contribution of AB is equal to 0, 0, 0, 3I by 4. Similarly, we can find out for BC, KBC is going to be equal to ABC transpose KBC ABC. Now ABC is equal to 4EI upon 5, 2, 1, 1, 2, sorry, that is K ABC, and A ABC is equal to 1 by 5, 1 by 5, 1, 0. So therefore, the first thing is KBC into ABC, and this is equal to 4EI by 5, 2, 1, 1, 2 into 1 by 5, 1 by 5, 1, 0, and this is going to be equal to 4EI by 5. You have 2 by 5, so 3 by 5. Here also you have 3 by 5. Here you have 2. Here you have 1. Okay. So the next step is to find out. So KBC is going to be equal to 1 by 5, 1 by 5, 1, 0 into 4EI upon 5, 3 by 5, 3 by 5, 2, 1. So this is going to be equal to 4EI by 5. This is going to be 3 by 25, 3 by 25. So it's going to be equal to 6 upon 25. This is going to be 3 upon 5. This is going to be 3 upon 5. And this is going to be 2. Okay. So what is the total K? The total K is going to be equal to 24 by 125. So this is going to be, K is going to be equal to 24 EI upon 125. This is going to be 12 EI upon 125, and this is going to be 12 EI upon 125, and this is going to be equal to EI into 8 by 5 plus 3 by 4. So this is my K, and therefore, and what's my R? If you look at R, R is going to be equal to 50, 0, and we haven't yet done the AI transpose into this thing, and so the AI transpose into SI0 is only there for AB, and this is going to be equal to 0, 1, AI transpose is 0, 1 into minus 300. So this is going to be equal to 0 minus 300. So ultimately my equation looks like this. It's going to be equal to 50, 0 is equal to 24 EI upon 125, 12 EI upon 125, 12 EI upon 125, and 47 upon 20 EI into R1, R2 minus 0, 300. So I can take this on this side. This implies that if I put EI outside, 24 upon 125, 12 upon 125, 47 upon 20, R1, R2 is equal to 50, 300. Okay, so this we solve for R1 and R2, from which we can find out our SI, because SI is equal to Ki AI into R. Okay, and once we find out the member end moments, we can always draw the bending moment diagram. Okay, so this is a fairly simple specific problem, and therefore there is not too much in it. Let me change this problem a little bit, and then we can solve another problem with it, because the essential thing that happens in this particular case is that we need to be able to find out how a change can be incorporated in the entire problem statement. Let me change this problem and let me give it as a slightly different problem, and the problem that I'll give you is this one. So this is another example. Here this is the same, excepting that now what I have done is I have now done this. So this particular, which was vertical here, I have inclined it. Okay, and this is a same Now here you see this point can actually move in this direction, you can see. So I'm going to define, instead of the horizontal, I'm going to define the vertical as my displacement, degree of freedom. Okay, you can define it horizontal also, there is no problem. So this is 2EI and this is still 4 meters. Okay, the only difference here is that this is going to be equal to 3 meters and this is equal to 4 meters. So the total length is still 5 meters. It's just inclined. Okay. So if we do that, then what do you get? We get the fixed end moment still remains the same. And this is going to be, the fixed end moment is going to be equal to $100 multiplied by, this is going to be equal to, this is a very, this thing, it's going to be 100 into 4 PL upon 8. Okay, it's PL upon 8. So this is minus and then plus half of PL upon 8. So please make the correction even in the previous problem, so that instead of 300, what you have over here is minus 75 kilonewton meter. This is BA and FEM. So please make the change that in the previous case also this is minus. The same, there is no difference in the fixed end moments. In other words, by changing the structural configuration, the fixed end moments in the two members are not changed. Okay, the only thing is that in the previous case when I had done minus 300, that's wrong. It's actually what I had done was I had made a mistake. I had taken 100 to be the intensity rather than a load. So it's PL upon 8. So this is PL upon 8, half carry over from the other side, and therefore this is minus 75, and these are two, the frequencies are different. Okay, now we come to the Ks. Okay, the K are also the same. K of AB is equal to 3I by 4 and KBC is equal to 4EI, because EI is 2EI. So it's going to be 4EI, 2EI, 2EI. Okay, so that's the stiffness for each member, and now we find out the A's. Okay, so for finding out the A, what do? I have this, and then I have this. Okay, now here R1 is equal to 1. So that means that now if you look at this, the only way this can move is along this line. Okay, perpendicular to this, and therefore for it to get one vertical, this will have to be 4 by 3 and this will have to be 5 by 3, and therefore this moves by 4 by 3. So this comes here and this one remains identical. So this is going to be like this and this is going to be like this. Okay, so and then when I put R2 equal to 1, I get the same as in the previous case. Note that here there is no moment restraint, so it can take any arbitrary. Here this is equal to 1, this is equal to 1, this is R2 equal to 1, and therefore we have AAB is equal to the first one. If we look at it, AAB is equal to, let us take stock of this, it's going to be like this, right? And this is going to be straight, so this is going to be clockwise. So AAB is going to be equal to 1 upon 4. Okay, now if you look at it, it's going to be clockwise, so it's going to be minus 1 upon 4, and for this one it's going to be equal to 1. A B C is going to be equal to, for the first one the total displacement is 5 by 3, and if you look at it anti-clockwise, so this is 5 by 3 divided by 5 is 1 by 3, so it's going to be 1 by 3, 1 by 3, and for this one it's going to be equal to 1, 0. Okay, so if we have that, so we've got the things, okay, and note that we also need to find out in this particular case, since we'll have how much does this point move by, so I'm not going to do AAB transpose, which is to see how much these move up by. So these move up, if you look at it, the A is equal to 0, this moves up by 0, and this moves up by 1. Okay. So if we look at it now, we've got the fixed end moments, we've got the K's, we've got the A's. Now all we need to do is find out the contribution of each one. So if I want to write down, I'll write it down as AB is equal to K A into minus 1 by 4 1 R1 R2 plus, and if we look at this is going to be minus 75. Okay, and SBC is equal to 4EI upon 5 2112 into 1/3 1/3 1 0 into R1 R2. Okay, so and plus 0. Okay, so this gives you this is MAB and this is MBC and MCB. Okay, so these are the things, and then all we need to do is, so this relationship will come out to be important. Here, this one, this part which I'll call as TAB, and this part which I'll call as TBC. So TAB is equal to minus 3I by 16 and 3EI by 4. In other words, this into the R1 R vector will give me SAB. Okay, and TBC, if you look at it, it becomes 4EI upon 5. In this, 2/3 plus 1/3 is equal to 1. Here you will have 1/3 and 2/3 1. This way you get 2. This way you get 1. So this is TAB and TBC. Okay, and now once we have that, we can find out KAB as essentially AB into TAB, and similarly KBC is equal to this. So this, if we find out, we get it equal to, what is AAB transpose? You will see that this is equal to 1 upon 4 1, and TAB is equal to minus 3EI by 16, 3EI by 4. So this is equal to, this way you get 3EI by 64. This way you get minus 3EI by 16. Here you get minus 3EI by 16, and this way you get 3EI by 4. So that gives the contribution of member AB to the structure stiffness matrix. Okay, so we have evaluated the contribution of the member AB to the structure stiffness matrix. The next step is finding out the contribution of the member BC to the structure stiffness matrix, and this is equal to ABC transpose TBC. So that is equal to 1/3, 1/3, 1, 0, and multiplied by 4EI upon 5, 1, 1, 2, 1. So this is equal to 4EI upon 5. I get 1/3, 1/3, 2/3. Here I get 1, here I get 1, and here I get 2. So this is the contribution of the member BC to the structure stiffness matrix. Okay, so if we put it together, what we actually get over here is equal to, let's see what we get. We're going to put it together to get the K matrix, and the K matrix is going to be equal to uh, 3 by 64 plus 8 by 15. So I'm going to put EI outside. So this is going to be 3 by 64 plus 8 by 15. Then we have minus 3 by 16 plus 4 by 5. Then we have a minus 3 by 16 plus 4 by 5, and then we have 3 by 4 plus 8 by 5. Okay, so what we get over here is equal to, K is equal to EI into 0.5802. This is going to be 0.6125 minus, plus This is also plus. This is 0.8 minus 3 by 16, so this becomes that way. And this is plus 0.6125. And this one becomes 1.6 plus 0.75 is 2.35. That is your K. Okay. Now let us see what happens to AI, the AIN. So one part is computing AAB into SAB 0, which is the fixed end moment. So if we do this, this part AAB transpose is equal to minus 1 over 4 1, and SAB is equal to minus 75. So this is equal to, on this side 17 by 4 is 18.75 minus 75. This is one. And the other one that we have is the work done by the AI. So this is going to be AAB transpose into NAB 0. And this, if you look at it, what was AAB? We had computed AAB. You remember? We'll just go back to that. That was equal to 0, 1. So this is 0, 0, 1, and then 0, 0. For R2, this is going to be 0, 0. So this multiplied by, what were they? 50, 50. So what we get is corresponding, I'm so sorry. This is corresponding to the second one, and this is 0, 0. So what we get over here is that this is equal to 50 and this is equal to 0. Okay, so ultimately when I put it all together, you will see that now I'm going to put everything together. And so what I have over here is R, which is 50, 0, is equal to K. K is equal to EI into 0.5802, 0.6125, 0.6125, and 2.35 into R1, R2, then I have plus 18.75 minus 75 plus 50, 0. So what we have over here is the fact that in this particular case, you will see that when I do on the other side, I get it equal to EI into 0.5802, 0.6125, 0.6125 to R1, R2, I made a mistake here. Look at this. This is not 50. Why? Because even this one, I need to find out, see, my R1 is my vertical, so the 50 is horizontal. So I need to find out how much this has moved by. So this is going to be 4 by 3. Okay? So when you have 4 by 3, okay, you're going to have it equal to so this is going to be equal to 50 by 3 minus 18 by 5. Okay, so this is going to be equal to minus this is 68.5, and here you have 50 by 4, so this is equal to minus 50 by 3 minus 18 by 5. 50 by 3 is equal to 20, so this is going to be equal to just bear with me, 16.67, so this is going to be equal to 2.08, and this is going to be 75. Okay, so now we can solve. So we get, if we get here R1 and R2 turns out to be equal to 1.018 upon EI, 2.35 minus 0.6125 minus 0.6125, 0.5802 into minus 2.08 into 75. If we do that computation, we get it equal to minus 51.434 EI, and this one works out to be 45.321 upon EI. Okay, so we've got R1 and R2, and now if I were to plot this one, how would it look? R1 is negative, okay, so which basically means that it actually comes down, okay, and anti-clockwise. So if I were to show that to you, okay, it would look something like this. This is my so in other words, this is of course exploded. So this vertical, it's actually moved down. In other words, it can't move down, so it will have to move this way also. So this point is actually come here, where the vertical displacement is equal to 51.434 EI. Okay, from that we can find out this displacement, and furthermore this has rotated in a anti-clockwise manner. In other words, it's gone this way. So what we have over here is okay, this will have moved over here by 4 by 3 times this. Okay, so this has moved by 4 by 3 into 51.434. This is this distance, and this one is going to look like this. So this rotation from the horizontal, this rotation is equal to 45.321 EI. And if you were to look at it from this, this is also equal to this from the original. Okay, this gives you the displaced shape of the structure. Okay, and finally, once you have that, you can plug in the R1 and R2 values into the expressions, and we get MBA is equal to minus 31.365 kilonewton, MBC is equal to 31.365, and MCB is equal to minus 4.89 kilonewton meter. Now, if I were to draw the bending moment diagram, and that's the last thing that is part of this thing, and if you were to draw the bending moment diagram, we know the member end moments. So this is clockwise. Clockwise means this way. So I'm going to draw it on the tension side. So this would be this way, and this one, if it's this way, is this. So this one also goes here. So we have 4.89, 31.365, and the bending moment is in this way. And then if we go here, this is also 31.365, and here we have 0. So we have this, and then I superpose on that the 100. So this I get this way and this way. This one is in this manner, this one is in this manner, and therefore what we have here is, at this value, you can check it, will be equal to 84.32. Okay, so this is the bending moment diagram, and that in essence is the complete solution of this method. Now, I have gone through all the steps in this particular case. I would like you to go back and revise these steps so that you can be confident how to apply the displacement method. Okay? Thank you very much. See you in the next lecture.